We know that there are two types of indexing, single level index and multi-level index. In single level indexing, there are three types of indexing methods: primary indexing, clustering index, and secondary index. And in multi-level indexing, we will see the B-tree and B+Trees. Index update in insertion. When we insert uh, a new entry in single level indexing, um, it perform a lookup using the search key value appearing in the record to be inserted. um, when the dense in the dense index, we know that if an index entry is created for every search key value, then it is called as dense index. In this insertion, if the search key value does not appear in the index, we have to insert it in the dense index. We know that sparse index is the um, if an index entry is created only for some records, then it is called as sparse index. But a dense index and sparse index are not complement to each other. You know that if an index stores an entry for each block of the file, there is no change needs to be made to the index unless a new block is created. In this case, the first search key value appearing in the new block is inserted into the index. In multi-level insertion, algorithms are used in as a single level indexing as an extension. An index update deletion. If I delete a record, was the file with its particular search key value, the search key is deleted from the index also. In single level deletion, in the dense index, deletion of search key is similar to the file record deletion. In sparse index, if an entry for the search key exists in the index, it is deleted by replacing the entry in the index with the next search key value in the file. The next one is indexing. Let us assume that already one primary index is existing in a relation. Only this key is suitable only when we write the queries based on that key, that is primary index value. Um, when we write a query based on some field, then the primary key index is not helpful. It only helps when we write a query based on a key value with the primary key field. When the query is uh, based on some field attribute, it may be frequent, then we have to maintain an index file based on that field. uh, in this field, this field may be unsorted because the data file is already sorted based on primary key field attribute. The index file um, based on this field should be sorted, and each key value in index will have one access on data file. In index file, there may be searching may be on binary search, and secondary index provides a secondary means of accessing a file for which primary access already exists. And index created for each record in a file, it may be a dense index, and the number of index entries will be equal to the number of records in secondary index. In primary indexing, the primary key should be ordered, and a primary index is an ordered file whose records are fixed length with the two fields. The first field is same as the primary key of data file, and second field is a pointer of data block where the key is available, and it has a block anchors. Index created for first record of each block is called as block anchors. Mm, and the number of index entries is equal to the number of data blocks, and the average number of block access using the index log to b plus 1, that is b means number of index blocks. Then we move on to uh, B-tree and B+Trees multi-level indexing. It is B and B+Trees are the generalization of uh, multi-level indexing. These are multi-level indexes with small modifications. We have to know some of the terms in B-trees and B+Trees. That is node pointer or block pointer, then record pointer. It is a pointer points to the record we are searching for within the block. Okay. Before we move into B+Trees, we first know what is block pointer and record pointer. A block pointer is a node pointer, or it points to a particular block, and a record pointer points to the record where we are searching for within the block. So in B trees, at every level we are going to have key and data pointer, and that data pointer actually pointing to either block or record. In B+Trees, um, it has an index structure is most widely used for several index structures that maintain their efficiency despite for insertion and deletion of data. It takes the form of balanced tree in which every path from the root of the tree to a leaf of the tree is of the same length, and each non-leaf node in the tree has between n by 2 and n children, where n is fixed for a particular tree. The main disadvantage of the index sequential file organization, the performance degrades as the file grows, both for index and for sequential scans through the data. So we are moving for this B+Tree index files. This is the B+Tree node structure. This is the typical node of B+Tree. This figure shows the structure of B+Tree. It contains up to n-1 search key values, k1, k2 up to kn-1, and n pointers p1, p2 up to pn. The search key values within a node are kept in sorted order. And this figure shows one leaf node of a B+Tree for the account file, in which we have chosen n to be 3, and the search key is branch name. The account file is ordered by branch name. The pointers in the leaf node point directly to the file. Each leaf can hold up to n-1 values. We can allow leaf nodes to contain as few as n-1 n minus 1 divided by 2 values. uh, the range of values in each leaf do not overlap. um, if the B+Tree index is to be a dense index, every search key value must appear in some leaf node. Since there is a linear order on the leaves based on the search key values they contain, we use Pn to chain together the leaf nodes in search key order. This ordering allow efficient sequential processing of the file. The non-leaf nodes of the B+Tree form a multi-level index, that is sparse index on the leaf nodes. A non-leaf node may hold up to n pointers and it must hold at least n by 2 pointers. So the number of pointers in a node is called as fan out of the node. The root node can hold fewer than n by 2 pointers. N by 2 pointers, and it must hold at least 2 pointers unless the tree consists of only one node. It is always possible to construct a B+Tree for any n that satisfies the requirements. And this figure shows a complete B+Tree for the account file for n equal to 3. And this one shows a B+Tree for the account file with n equal to 5. These examples of B+Trees are all balanced, and the length of every path from the root to a leaf node is the same. This property is a requirement for a B+Tree. The B in B+Tree stands for balanced. It is a balanced property of B+Trees that ensures good performance in insertion and deletion. In processing a query, we traverse a path in a tree from the root to some leaf node. If there is a search key value in the file, the path is no longer than log n by 2 of k. Suppose we wish to find all records with search key value of v. Search key value of v. A procedure, it works. First we examine the root node looking for search key value greater than v. Suppose that we find that the search key value is ki. We then follow pointer pi to another node. If we find no such value, then k is greater than or equal to k m minus 1, where m is the number of pointers in the node. In this case, we follow pm to another node. In the node we reached above, again we look for the smallest search key value greater than v, and once again follow the corresponding pointer as above. So eventually we reach a leaf node. At the leaf node, if we find search key value ki that equals the v, then pointer pi directs to the desired record or bucket. If the value v is not found in the leaf node, no record with the key value v exists. So this is about query on B+Trees. Then this is about insertion in B plus trees. We have to, if we want to insert a node in a B plus tree, first we have to find the leaf node in which the search key value would appear. If the search key value is already there in the leaf node, record is added to file, and if necessary, a pointer is inserted into the bucket. If the search key value is not there, then a record is added to the main file and bucket is created. Uh, if there is a space in leaf node, we should insert the key value pointer in leaf node, otherwise we have to split the node. For splitting a node, it takes n pairs in sorted order and place the seal of n by 2 in the original node. Place the first seal of n by 2 in the original node and the rest in a new node. And let the new node be P and let K be the least key value in P. Insert in the parent of the node being split, and if the parent is full, split it and propagate the split further up. The splitting of nodes proceeds upwards till a node that is not full is found. In the worst case, the root node may be split, increasing the height of the tree by 1. And this is B plus tree before and after insertion of a clear view. And when we want to delete a node in a B plus tree, find the record to be deleted and remove it from the main file from the bucket, and remove from the leaf node if there is no bucket or bucket has become empty. If the node has too few entries due to the removal, and the entries in the node and a sibling fit into a single node, then insert all the search key values in the two nodes into a single node and delete the other node, and delete the pair ki minus 1 and pi, and pi is the pointer to the deleted node from its parent, and recursively using the above steps. Otherwise, if the node has too few entries due to the removal, and the entries in the node and the sibling fit into a single node, then we have to redistribute the pointers between the node and the sibling such both have more than minimum number of entries, and update the corresponding search key value in the parent of the node. This deletions may cascade upwards till a node which has seal of n by 2 or more pointers is found. If the root node has only one pointer after deletion, it is deleted and the sole child becomes the root. This is the before and after deleting downtown. The removal of the leaf node containing downtown did not result in its parent having too little pointers, so the cascaded deletions stopped with the deleted leaf node's parent. Here, the peri-ridge is deleted. Node with peri-ridge becomes underfull and merged with its siblings. As a result, peri-ridge node's parent became underfull and was merged with its sibling. Root node had only one child and was deleted, and its child became the new root node. So this is all about B plus trees, insertion and deletions. Thank you.